Hello, I'm Ojasvi. Today I'll be speaking to you about my final year project that I did at Monash University. In 2017, Monash University outlined an ambitious goal that by the year 2030, all energy used on all Monash University campuses will be clean and renewable. This is called Project Net Zero. To achieve this project, solar panels have been installed all around the campus, and in particular, the Department of Electrical and Computer Systems Engineering has installed a 10 kilowatt solar panel array, and that solar panel array has been connected to a microgrid to manage all that energy that's being absorbed. So my final year project was to develop a near real-time and reliable monitoring system for this microgrid to display the activity of the microgrid at any moment in time.
The monitoring system developed for the microgrid was required to be reliable and show near real-time activity of the system. This project aim was successfully achieved, with the final outcome eliminating the need for previously prescribed NC-DAC hardware for communication. Additionally, the communication between the LabVIEW program and the microgrid is capable of communicating over the local area network. Eliminating the need for a wired connection to the microgrid means that the 49-inch display monitor on which the monitoring system runs is not restricted to be at a close distance to the microgrid. So, the project aim was successfully achieved and extended upon by creating a HTML file of the LabVIEW program and eliminating the need for extra hardware.
So let me speak to you about the microgrid. Over here we have the microgrid, which has been configured into two unique microgrids, the SMA microgrid and the Selectronic microgrid. So let me first speak to you about the Selectronic microgrid. Here we have a hybrid Selectronic inverter which interfaces with the power grid as well, and that's been connected to 4 lead acid batteries in the black box over here, and also connected to this ABB inverter. So this ABB inverter receives the actual solar panel power. So let me now talk to you about the SMA microgrid. Here we have the Sunny Boy inverter, which receives the solar panel absorption. And over here we have the Sunny Boy storage, which manages the LG Chem battery. Here we have a SMA cluster controller, which acts as the main communication hub of the whole SMA microgrid. And inside here we have the SMA energy meter, which is the interface between the SMA microgrid and the power grid. So let me now speak to you about the monitoring system that I developed.
The monitoring system was developed on LabVIEW. LabVIEW is a graphical software program, not requiring the user to develop written code, instead have an understanding of written code to apply in a graphical format. A LabVIEW program has two interfaces, one called the block diagram, where all the code is developed, and the other called the front panel, which acts as a user interface. I'll first go over the block diagram developed, which acts as the brains of the monitoring system. The main code is inside a while loop, which is represented by this dark grey box over here, and will keep running till the stop button of the program is pressed. In LabVIEW, code runs from left to right, so let me begin on the left and explain my way through. The developed monitoring system gauges the activity of the microgrid by communicating with 4 devices from the microgrid over an Ethernet connection. The first one is a Selectronic inverter, the second is a Sunny Boy storage, the third is a SMA cluster controller, and the fourth is another cluster controller, part of another project. All 4 connections are made by LabVIEW in parallel. So the bottom 3 device connections, which I just showed, have an almost identical process run through. So I'll first begin by speaking about the Selectronic device connection. Actions inside the while loop are governed by a shift register, which decides the case to run over here, where different cases represent different parameters. For example, case 1 finds the lead acid battery state of charge. So after the connection between the LabVIEW program and Selectronic is made, the code enters this area. Here, the address where the battery state of charge parameter is held in the device is written to the device for access, and data written back from the device is read. And in this application, only the 8th and 9th bit out of the 12 bits sent back by the device are the data bits, so they're selected and sent through to the next stage of the process. And in the next stage, some calculations are done to decipher the received data bits. The result can also be further analysed like I have done so over here. And that is how one case or parameter from Selectronic is monitored. Implementation of the case structure then occurs in this little section here, all the way up till case 21, where a fresh value of 1 is assigned in the shift register for the whole process to run once again. So this occurs infinitely till the stop button of the while loop is pressed. So moving on now to the next 3 resource communications, which all follow a very similar process. So in the Selectronic case, data communication protocol VISA was used to communicate to RS-232 over the local area network, but in the SMA case, TCP/IP has been used. So let's quickly go over one interaction again, but now for SMA. So after configuring connection between the LabVIEW program and the SMA device over here, we move on into the while loop. Again, the case statement governs which parameter is monitored. There is an extra step before polling a device. So over here we can see that a unit ID has to be specified as there are multiple slaves. After that, correct configuration of sending and receiving data is done in this block over here. And also the address and how many bits are required is written over here. And there is an error handler right over here as well. So if there are common errors encountered by the program at any stage, this case structure is entered. For example, error 1, 59 or 62. And the Modbus connection is shut down and reopened. And this goes into another shift register, which comes back into a loop over here. So this doesn't need to occur again. This error block is a very good tool to use to handle errors, especially common errors. Moving on, the analysis of received data from the device is done in this stage over here. Similar to above where we had a numeric bar to represent the battery's charge status, we do so here as well. And then we have another case structure to increment the case, which is repeated and done indefinitely till the stop button of the while loop is pressed. So we can see over here that identical processes run in parallel for the other 2 Ethernet devices or SMA devices. Over here I'm just doing some calculations and analysis of other parameters to come up with new parameters to provide greater insight into the activity of the microgrid. Now moving down here, I've used a dark sky API, a LabVIEW API to show daily weather data in my front panel. So basically I'm showing the maximum and minimum temperatures as well as a daily forecast summary, and alongside that I'm showing an icon which shows visually what the weather will be like for today, for example sunny or cloudy or rainy. Now moving towards the right, you will see shortly in my front panel I have 5 pages, and I cycle through the 5 pages every few seconds. So over here this is how I've defined it, that there's a for loop, and for each page run the page for this number of seconds. So this is actually milliseconds, so this right now says run each page for 12 seconds and do that for all 5 pages, and because this is in a while loop then it runs indefinitely. So those were the main aspects of the block diagram for the monitoring system, and I'll now move on to the front panel. This is the front panel or the user interface of the developed monitoring system. It shows near real-time activity of the Selectronic and SMA microgrid over 5 pages. Let me first reinitialize all the values to 0 so that I can demonstrate the working nature of the file. I've also created a HTML file, so let's check everything is 0 there too. The HTML file mirrors the LabVIEW file. So you can see everything is 0. Now running the file. The first page is titled Technical Information. It shows photos of the microgrid devices with some important parameters next to them. The next page shows the activity of this electronic microgrid, and the page has been split to provide load, grid, battery, and weather information. This page is almost identical to the previous, showing details of the SMA microgrid. Again, it has been split to provide load, grid, battery, and weather information. This page shows Selectronic's days breakdown, how much power has been supplied from grid and solar, and of this how much has gone to charging batteries, powering loads, and exported back to the grid. And this last page shows graphs of the instantaneous solar output power for both Selectronic and SMA. The Y scale is auto-scaled and the X scale ranges from current time plus 14 hours. It is intended to run this at 7 AM to go till 9 PM. The chart resets at 6:59 AM every morning. You can see I'm on the Google tab, and there are some additions to this. So I've got a title here as well, Monash Uni Building 35 Microgrid Monitoring System, and down the bottom my name as well. So let's make this full screen. You can see the values are updating regularly, just as if we're on the LabVIEW program itself. Taking this one step further, creating the HTML file was great. Allows for a better user interface as well. I'm showing a 49-inch screen.
Software programs are almost never finished pieces of work. There can always be a better user interface and more features included. The monitoring system developed is in essence at a complete stage, as it has achieved its project goals. However, there is greater potential to take it further. As mentioned, a HTML link was created for the monitoring system. In the future, the monitoring system can be developed such that anyone with a certain URL can view the program from anywhere in the world. This may be possible by developing a local server onto which the program feeds in, and a web page which receives real-time updates from the server. This would require close work with the Monash University IT department to ensure its possibility with the network security systems in place. Additionally, the configuring of the microgrids are bound to change. This may require monitoring of additional parameters in the future which are not yet in place. At the moment, as the microgrid components are fairly new, only the activity of the microgrid is being monitored. Sometime in the future, the health of the devices can be monitored as well to ensure the power from the PV array is managed correctly. This brings us to the end of the presentation. Undertaking this project has been an eye-opening experience in the necessity and importance of monitoring processes and systems in place. I am greatly appreciative to Monash University's ECSE department for their continual guidance and support during the project, and I look forward to even greater initiatives being undertaken by the department in the future. Thank you for watching.